Next, let us discuss the different situation. That is, if the observer is stationary and the source moves toward or away from the observer. Since the sound wave moves independently from the motion of the source, so in this figure, if the source here generates the sound wave and the wavefront of the sound wave moves toward this observer and also this observer, and once the sound wave generate once the source generate the sound wave, it moves toward the observer A, and it continue generate the wavefront that move toward the observer A. We can see that if we look at the peak of the wave that move toward to A, the source will generate the wavefront of the peak at the point that nearer to the observer A, which means that the wavefront of the source that moves to the observer A will be closer. It will be closer if we compare to the wavefront of the source if the source is also stationary. And we can also see that for this observer that the source moves away from the observer B, we can see that the wavefront that go to the observer B will have the larger lambda, the larger wavelength than the wavefront, the distance between adjacent wavefront if the source is stationary. Okay. The figure on the right shows the real situation when we have the source of the wave generate the water wave in the wave tank, and this source move toward to the observer at C. We can see that the wavelength in this side is smaller, is small, and the wavelength on this side is larger than the wavelength on this side, and this is because this is the effect of the movement of the source. Now, let us see the situation that the source moves toward to the observer. If the wavelength from the stationary source is lambda, and the wavelength from the moving source is lambda prime, and we can see that lambda prime is less than lambda, and we also know that the source will generate the new wavefront every time the new wavefront with the same phase every period of the oscillation. Okay, it will generate the wavefront with the same phase every one period. So it means that if we look at the wavefront with the same phase, this wavefront and this wavefront, between these two adjacent wavefront, this wavefront will be generated when the source moves with the distance equal to the VST. Okay. We can say that for one period the source move with a distance VST. Here Vs is the velocity of the source, and it means that this wavefront will be generated when the source moves with this distance, and after that it moves independently from the source. So it means that the wavelength that this observer sees, which is the distance between two adjacent wavefronts that have the same phase, will equal to the difference of the wavelength if the wavelength from the stationary source minus the distance that the source moves during the next generation of this wavefront. So what we have is that the lambda prime, which is the wavelength that the observers A see, is equal to the lambda, which is the wavelength of the stationary source minus VST. Okay, because the adjacent wavefront with the same phase will be generated from the source when the source moves with the distance VST. Okay, and this is equal to the lambda minus Vs over frequency. This is the frequency of the sound wave at the source. I mean the source generates the sound wave with this frequency. Okay. However, since the sound wave moves independently from the source, so it means that this observer A will see the velocity of the sound wave, the same velocity of the sound wave as the wave that comes from the stationary source. So we must have that the velocity of the sound wave that the observer AC is equal to the velocity of the sound wave for the stationary source, but for the observer A it must equal to the F prime lambda prime. Okay. And also we can relate the velocity of the sound wave for the stationary source as the F lambda. Okay, and from these two equations we can have that f prime is equal to the f lambda over lambda prime. Okay, or we can have that this equal to the f lambda over lambda minus vs over f. Okay. And from this equation you can see that we can cancel this lambda and this lambda, but we have to put this lambda here. Okay, and what we have is that f prime is equal to the f over 1 minus vs over v. This one comes from the fact that this term f lambda is equal to v. Okay, or we can have that this equal to the v over v minus vs times f. So this is a situation that the source moves toward the observer. Okay, and using the same procedure we can see that if the source moves away from the observer, we must have that in this situation f is equal to the v over v plus vs f. This is for this situation. So we have the formula for the Doppler effect when the source moves toward or move away from the observer. Now we will combine those four formulas for the frequency that the observer will hear if the frequency moves toward or away from the source, and when the source moves toward or away from the observer. We can write down the combined formula as f prime is equal to the v plus vo over v minus vs times f. In this formula, v is the velocity of the sound wave from the stationary source or we can say the better word is not the stationary source, from the stationary medium. The stationary medium. So if we have the medium with that stationary, and we measure the velocity of the sound relative to the stationary medium, and the velocity of the sound is equal to v. Okay. Next, we have that VO is the velocity of the observer and we use the sign convention that VO is positive if the observer moves toward the source, and VO is negative if the observer moves away from the source. Okay. And next we have Vs is the velocity of the source. The velocity of the source. Now we have that Vf is positive if the source moves toward the velocity, the observer. Okay. And we have Vs is negative if the source move away from the observer. So we can use one formula. To explain the Doppler effect with the appropriate the sign convention here. Okay, the sign convention here.